Hello and welcome to the last video which supports microeconomics for business and its mathematical skills. Today we are going to talk about differentiation and the use of differentiation in microeconomics. During this video I will remind you of the gradient of a straight line, and then from there we're going to talk about what is differentiation. Then I'll introduce you to the basic rules of differentiation. We're going to do quite a few practice questions so you become familiar with this concept and calculation of differentiation. Then we're looking at the applications in microeconomics. We're going to look at marginal quantities, and we're going to spend quite some time on the perfect competition. So let's start with the gradient of a straight line. We already talked about it in a previous video when we talked about the graphs, especially the linear graphs. So this concept should be somewhat familiar. So what was the rate of change? Well, remember that we were talking about the gradient being the change in y over the change in x, which we could have calculated by y2 minus y1 over x2 minus x1, where these are the coordinates of two different points on the straight line. And this concept could tell us the slope, which was the steepness of the graph. But that's exactly the same as how fast something is changing. So let's look at a couple of special cases. I have got a constant function here. Constant means it has got the same value at every single x point, so it's constant, it's the same. But that name kind of gives it away. Constant doesn't change. So the rate of change of a constant function is 0. So a constant function's m is going to be 0, simply because if you think about any 2 points on this graph I can pick out, point 1 and point 2. This is the x1 coordinate, this is the x2 coordinate, but look at the coordinate, the y coordinate is the same for both of them. So this difference of y2 minus y1 is 0. So 0 divided by anything will always going to give me 0. So the constant functions, which you intuitively sort of see that it's a non-changing function, mathematically or algebraically you can also see that the rate of change here is 0. How about the linear graph? So if you look at a linear graph, that would look something like this. So the rate of change here again, I've got point 1 and I've got point 2, and I have got the corresponding coordinates. This is x1, this is x2, and that is y1, and that is y2. So there is some kind of change in here, because I can actually visually show you that this would be the delta x, that's the x2 minus x1, and this would be the delta y, which is the y2 minus y1 distance. And basically the rate of change is how far I'm going up on the graph. So for a linear graph, as we established in the previous video, the rate of change is the same, doesn't matter which 2 points I'm looking at. So why is this actually good for us? Well, this is good for us because we can extend it to non-linear graphs. So if I have got a curvy graph or curved graph, something like this, well, I can intuitively see that this graph changes differently at different points. So let's say I'm picking up a point. This would be point P. So what is the change at this point? Well, we know how to calculate the change for linear graphs, and we know that every curve looks linear if we look at it close enough. So using those two intuitions, well, I can say, okay, I can choose a point close enough to P, let's say here, call it P prime. And if I join these 2 points, then I have got a line. And that line I can calculate the gradient of, and that would be close enough to the change, but not exactly. So what happens if I start to bring this P prime point closer and closer to the original P point? So let's say I would choose this point here, P double prime. Well, if I look at this here, it's a lot more closer approximation to the curve than the previous was. So the rate of change of this line is much better description for the rate of change of the curve than the blue one. But I can take it to the extreme. I can bring that P prime to as close to P as it's literally the same point. But what happens to that line there? Now that line that is a chord at the moment will become the tangent. And for every point on any curve, I only have got one tangent. I mean, I can have many different chords depending on which other points I'm choosing, but I can only have one tangent. And a tangent is a straight line which touches the curve only at one point, nowhere else, just one point. And that is very useful for us because then I can calculate the change of this tangent, and that will describe me the change of the function at this particular point. So I got a concept now to describe the change at one point. But what happens if I look at a different point? Let's say pick Q here. Well, I can go through the exact same thought process. I can pick a point here. I can say, well, that's Q prime, describing the change, but I can bring it closer, Q double prime, and that will be again a better approximation. But the best of it to describe the change at Q will be the tangent at Q. So again, we can see that the 2 points P and Q are at very different stages of the curve, therefore the rate of change will be very different. But using the gradient of the tangent, we can always describe the change at that particular point. So now we know the change at one point, but that's not really helping us because we want the change to trace it across the whole graph. So going through every single point and calculating the gradient of the tangent at every single point can be quite daunting. Therefore, mathematicians over the years developed a technique called differentiation. And for those differentiations, you just need to remember a few simple rules and you will be able to find the rate of change or the change function, the derivative function, for any possible functions. Now, before I go into these basic rules, I'd like to draw your attention to the different notations. Unfortunately, differentiation has been developed independently by at least 3 different mathematicians back in the 16th, 17th centuries. So up to today, we have got 3 different notations for differentiation. The first notation is read y prime equals f prime of x, which has been introduced by Lagrange. The second notation, which is read dy dx or df dx, minding it's not a division, so it's not dy divided by dx, it's dy dx, and it's just showing you that you're carrying out the differentiation rather than division. It's been introduced by Leibniz. This is probably the one that is most commonly used. And the last one, the dot notation, the y dot equals f dot of x, is being introduced by Newton. So it's very commonly used in physics, as Newton developed a lot of very interesting concepts in physics as well. So let's look at the basic rules of differentiation. So if I have got a constant function, and I can refer to that as y equals c, c referring to constant, then the derivative of that, the dy dx, therefore would be 0. Now, the simple reason why is basically, remember, I'm just going to do the sketching here so you can see it yourself, but remember, the constant function does not change. And what do we do by differentiation? With differentiation, we're trying to find out the change in the function. Well, the constant function doesn't change, so the constant function's change or derivative always going to be 0. Now that constant can be any number. It can be 3, can be 7, or it can be down here. It can be minus 17 or minus 25. Doesn't matter, as long as this is just one number, the derivative always going to be 0. Now another one which is very important for us is the linear function. So if the linear function is equals ax plus b, or sometimes mx plus b, when we are talking about it as a graph, we usually refer to it as mx plus b, but the important thing is here we just got a constant in front of the x and another constant added. It could be 0 sometimes, so if I have got y equals 3x, that's also a linear function. It's just going through the 0, the origin, rather than being pushed up or down. Now that's derivative, the dy dx is going to be a. Again, why? Well, the differentiation measures the change. And what is the rate of change of a linear function? Is the number in front of the x, the coefficient of x. So that's why the derivative is a. But again, if you think about it graphically, here is your linear function, and depending on what steps you're going, this change here, it's always going to change by a. And I'd like to mention a special case here. If y is just equal to x, then the derivative of that function is going to be 1. Again, try to think about it in graph format. So y equals x is basically all the coordinates are the same. So it's 1, 1, 2, 2, 3, 3, 4, 4. So it's a straight line going through the origin at a 45 degrees angle. So if I'm talking about the change in the function, it's 1, 1, 1, 1, 1, 1. So the change always going to be 1. Now, we introduced a couple of simple rules. Let's practice them. So, question number 1. If y equals 7, what is the derivative? So, what is dy dx? Well, 7 is a constant. That means that my function doesn't change. So, its derivative will be 0. Y equals minus 2. The same scenario. It's although a different number, but it's still a constant. So this function's derivative, which is the measure of the change, also going to be 0. Y equals 13, another constant. So the derivative again will be 0. Y equals minus 150, although that's a very big number, but it's still a number, so it again doesn't change. Its derivative will be 0. Number 5, a little bit of a difference now. This one is a linear function. So remember, what was the change or the derivative of a linear function? That is just the coefficient in front of the x. So that is equal to 2. Question 6, y equals 5x minus 2. This is again a linear function, so the derivative just will be the coefficient in front of x, so the derivative is 5. Number 7, y equals minus 2x plus 5. The derivative is going to be minus 2, because that is the number, that is the coefficient in front of x. Number 8, y equals a half x minus 7. So the derivative equals to a half, because that is the coefficient in front of x. Number 9, minus 2/3 of x minus 4. So the derivative is minus 2/3, coefficient in front of x. And the last example, y equals 20x plus 30. So the derivative is 20, because that's the coefficient or number in front of x. So they are not that complicated. Constants don't change, so the derivative always going to be 0, and the linear function's derivative is always just the coefficient in front of x. I'm going to introduce you to one more rule of differentiation. Now, differentiation can get a bit more complicated, because you can introduce then all sort of different kind of functions, product functions, quotient functions, logarithmic function, exponential functions. So if you want to take differentiation further, you can look at other videos and learn a little bit more about it. But knowing these three basic rules, the constant, the linear functions, and the power function I'm just going to introduce you to, will be enough to carry out calculations in microeconomics for business. If you are interested, more than welcome to go and look into more details. But if you don't have time, don't worry, these are perfectly sufficient to help you through microeconomics for business. So what does the power function look like? Well, it's basically a to the x of n. So basically, the variable x is raised to some kind of power, and we may or may not have got a coefficient in front of it. What will be the derivative? So the rule says bring the power down and lower the power by 1. It looks a little bit more complicated than it actually is, so I'm going to go straight into some practice questions to show you how simple this is. So if my function is 2x squared, then what do I need to do to calculate or find the derivative? I need to bring the power down, so 2 times 2, and I need to lower the power by 1. So 2 times 2 makes it 4, 2 minus 1 makes it 1, but x to the 1 is just x, so the derivative is actually 4x. Second example, y equals 5x cubed. So what is the derivative of this power function? Rule again, bring the power down and lower the power by 1. 3 times 5 makes it 15, and 3 minus 1 makes it 2. The third example is y equals 3 to the x half. So dy dx then will be bring the power down and lower the power by 1. Now 3 times a half gives me 3 halves, but what is a half minus 1? I'm going to calculate here. A half minus 1. When I need to take away fractions, I need to make sure that they have the so-called common denominator. So a half take away, I need to change the 1 into halves. So how many halves there are in 1? Well, a whole is 2 halves. So it's basically 1 half minus 2 halves. So a half minus 2 halves is basically going to be equal to a negative half, because I don't have enough to take 2 away from it. 1 minus 2 gives me negative 1, and halves taking away gonna give me minus half. So the power will be minus half. Number 4, y equals minus 6 times x to the minus half. So the derivative, again the rule, bring the power down and lower the power by 1. Multiplication, and I kept the bracket because I'm multiplying negative numbers. So negative times negative gives me positive. 6 times a half is 6 halves. And again, what is the power? So minus a half, take away 1. I again have to go through the same process of having this common denominator. So minus half minus 2 halves, which is my whole. Now in this case, what happens now? I have got a half, a negative half, and I'm taking away 2 more of those halves. So I was already in debt and I'm paying more money out. So altogether I'm going to end up with minus 3 halves. And the last thing to spot here is that 6 over 2 is just 3. So it's 3 times x to the minus 3 halves, or minus 3 over 2. And the last example, y equals 2 over 5 x to the minus 5. So what is the derivative here? Well, bring the power down and lower the power by 1. So let's tidy this one up. Negative times positive makes it negative. 5 times 2 over 5, the 5 can cancel out. And what will be the power? I've got £5 debt and I'm paying out 1 more pound, so I'm going to end up with negative 6. So minus 5 take away 1 gives me negative 6. So the final answer in nice and tidy format is minus 2x to the minus 6. Now I kept to this very detailed writing out of following through the rule. If I was to do it myself, I wouldn't bother writing these things always out, because I know that minus 5 minus 1, it gives me negative 6, so I could actually skip this step. But I suggest that until you become very familiar with how these rules work, try to detail them out as much as it's helpful for you. If this one is too much and you find it's just confusing you, then don't worry about it, just write out minus 6 straight away, which I'm probably going to refer back to later on when we start to carry out the exact calculations. Now, there are a couple of more rules that I would like to introduce you to, but they're not necessarily any difficult rules. Basically, what these rules are telling me is if I have got a function that is a sum or a difference of 2 functions, then I can differentiate them term by term, which is quite useful because applying the previous rules that we learned, the constants, the linear and the power rule, just looking at each terms and see, okay, is this constant, is it linear, or is it a power? And then I could apply those rules to that particular term, move on to the next one, and then go through the same process again. So let's look at some examples. So y equals 7x squared. Well, there's no sum or difference in here, so I can just simply apply the power rule. So dy dx will be, bring the power down, so I would have 2 times 7, which I can calculate in my head to be 14. And what will be the power of x? 2 minus 1 gives me 1, but the power of 1 we hardly ever write out, so that's the final answer, 14x. Nice and simple. Let's just look at a couple of more of these examples to sort of get used to how to write them quickly. So if y is equal to minus 2x cubed, then what will be the derivative? Well, negative times positive gives me negative, 2 times 3 gives me 6, and then the power is 1 less than 3, which is 2. Third example, if y is equal to 13x to the minus 5, then what will be the derivative? Well, again, bring the power down, but that means I'm going to have to multiply a positive and a negative together, so that gives me negative. 5 times 13 is 65, and the power of x is minus 5 minus 1, which is minus 6. So this is how you can write out using the power rule without having to detail all these exact calculations and still having the same answer in a shorter, quicker way. Now let's move on to the new rules, the sums and differences. In example 4, y is equal to minus x squared plus 4x minus 10. So what's the derivative of this function? Let's look at it term by term. So the first term is a power function. So what I need to do, I need to bring the power down, so that will make it minus 2. And the power of x will be 1, which we don't write out, plus. These two terms together is a linear function. And the linear function's derivative is just the number in front of x. Remember, this is a constant, and constant's derivative is always 0. So that is the derivative of this quadratic function. 5. Y equals 2x to the 5 plus 3. So what is the derivative of this function? So again, looking at the first term, that is a power function. So the power rule says bring the power down and lower the power by 1. So if I bring the power down, if I bring the 5 down, 2 times 5 makes 10. And lower the power by 1, 5 minus 1 makes it 4. The second term is a constant, and constant's derivative is 0. So the derivative is just 10x to the 4. 6. Y is equal to 5x to the minus 2 minus 2x plus 17. What's the derivative of this function? But we can again look at it term by term. The first term is a power function, so bring the power down. Minus 2 times 5 makes minus 10, and lower the power by 1. Minus 2 minus 1 gives me negative 3. Remember, you were already in £2 debt and you paid out £1 more, so your debt increases. That's why we got minus 3 there. The middle term, minus 2x, its derivative, x's derivative is 1, so minus 2x's derivative will be minus 2 times 1. So that's minus 2. And the constant, the plus 17, its derivative is 0 because constant doesn't change. So the derivative of this function will be minus 10 x to the minus 3 minus 2. So example 7, y is equal to minus 2x to the 0.5 plus 5x. So what is the derivative of this function? Again, what is the rule? Bring the power down, so that will be minus 2 times 0.5. But you remember that 0.5 is half, so what's the half of negative 2? Well, that's just negative 1. And remember, we don't write the 1 out as a coefficient, so I can just write negative x. And now lower the power by 1. So 0.5 take away 1 will give you negative 0.5. Remember, you've got 50 pence, you're taking away a whole pound, you end up with 50 pence debt. So to the power of minus 0.5 plus, what is the derivative of 5x? Well, x's derivative is always 1, and 5 is a constant multiplier which stays, so the derivative of 5x is 5. And the next example, example 8, is y equals a half x to the minus 0.5 minus 7x plus 2. So again, what is the derivative of this function? We can look at it term by term. So the first term is a power, so we need to bring the power down, but we remember that 0.5 is a half. So positive times negative will make a negative, and a half times a half. Remember, when you're multiplying fractions, you need to multiply numerator by numerator and denominator by denominator. So a half by a half gives you a quarter. And what's the power? Well, minus 0.5 is the original power, I need to lower it by 1. So minus 0.5 take away 1 gives you minus 1.5. Again, remember that you are already in 50 pence debit and you're paying £1 more out. So altogether, you're ending up with £1.50 debit. Now we can look at these last two terms as separate terms, or we can remember that this is like a linear function. And remember that a linear function's derivative is always just a number in front of the x. So minus 7. And remember, in other ways, that the positive 2 is a constant and constant's derivative is always 0. So that's why we don't write that out. Two more examples. Example 9. Y equals minus 2/3 x cubed minus 4x to the minus half plus x. So what is the derivative? Again, bring the power down. Positive times negative will make it negative, and 2/3 times 3. Dividing by 3 and multiplying by 3 cancels each other out, so I'm just going to end up with the negative 2. But what will be the power of x? 3 minus 1 gives me 2. Second term, it's negative, but I'm bringing the power down, which is also negative. So negative times negative will make it positive. And 4 times a half, or a half of 4, is 2. So what will be the x's power? Minus half take away 1 gives me minus 3 halves, or minus 1.5. And what's the derivative of x? Remember that this was a special case. X's derivative is always 1. And the last example. Y equals 20x cubed plus 30x squared. So look at the derivative. Well, after all those fractions, these ones are quite simple. 3 times 20 gives me 60. X's power become 2, because that is less, because that is 1 less than 3. 30 times 2 gives me 60 again, and x squared becomes x, because 1 is 1 less than 2, but the first power we don't write out. So these are the general mathematical rules of differentiation, and these examples were intended to help you to learn the technique of differentiation. But the final goal is not just learning the technique of differentiation, but to be able to apply it in the microeconomical concepts. So where do we use differentiation in microeconomics? Well, differentiation is very often used when you have to calculate the marginal products. So for example, if the production function is given and from there you need to calculate the marginal product of labor or the marginal product of capital, you would be using differentiation. For the marginal product of labor, you would differentiate the production function with respect to labor, and for marginal product of capital, you would be calculating the derivative of the production function with respect to the capital. Two more other important marginal concepts that will come handy during calculation questions is how to calculate marginal revenue and marginal cost. And marginal revenue, by definition, is the derivative of the total revenue with respect to the quantity, and the marginal cost is the derivative of the total cost with respect to quantity. So let's look at some practical examples. Suppose the production function is given by Q equals 2K plus 5L. So I know that my production function is 2K plus 5L. What is the marginal product of capital? So the question is the marginal product of capital when 5 units of capital, so K is 5, and 10 units of labor, so L is 10, are employed. What is the marginal product of labor? So we've got two questions. we need to calculate first the marginal product of capital, and then we need to calculate the marginal product of labor. So recall the definition. The marginal product of capital is the derivative of the production function with respect to the capital. So in this case, I'm only interested in the change in capital. I'm not interested in the change in labor. So labor is held constant, and constant's derivative is always 0. So when I come back to the production function, I'm only interested in this term because that term becomes 0 when I'm differentiating it, because it will be constant. So what's the derivative of 2k? Is 2. See, importance here, doesn't matter if capital is 5 and labor is 10, the marginal product of capital will always be 2, because after differentiation, the variable k disappears. So it's independent of individual capitals and labors applied. Similarly, the marginal product of labor is the derivative of the production function, but now with respect to the labor. So now k is held constant. I should have written here that labor is constant. And because k is now constant, the first term in the production function will become constant, because I'm only interested in the change with respect to labor. So constant's derivative is 0, 5L's derivative is 5. And similarly, as to the marginal product of capital, for this particular production function, the marginal product of labor is independent of how many labor I'm applying. It's always going to be 5. Now that's not always the case, because you can have some production functions where after differentiation the variables are still present. So let's look at one such example. So suppose the production function is given by q equals k to the 0.5 times L to the 0.5. So this is a very different production function, because here now capital and labor are multiplied while before they were added. What is the marginal product of capital? So again, marginal product of capital is the question. Then 25 units of capital, so k equals 25, and 9 units of labor are employed. What is the marginal product of labor? So again, we have got two questions. First, the marginal product of capital, and second, the marginal product of labor. So again, what is the definition to calculate marginal product of capital? So MPK by definition is the derivative of the production function with respect to capital. Now, what is our production function in this specific case? Q equals k to the 0.5 L to the 0.5. Now, the important thing is here, when we're differentiating with respect to k, or when we're looking for the marginal product of capital, we keep labor constant. Now, what is that constant value? Well, that's been given to us, that's exactly 9. So I can rewrite my production function as k to the 0.5 times 9 to the 0.5. Now again, I remember that 0.5 is a half, so 9 to the 0.5 is the same as 9 to the half. And I again remember that the half power is the root, the square root of 9, which is 3. So this exact production function is 3 times k to the 0.5. Now that looks a little bit simpler, so let's differentiate it. So constant stays, bring the power down, so that will be 3 times 0.5, and lower the power by 1. By now you should know that 0.5 take away 1 gives me minus 0.5. So that will be 1.5 times k to the minus 0.5. Now this is the marginal product of capital function, because it still depends on k. But the question was, what is the value of the marginal product of capital when this capital and this labor is applied. So there is one more step in here that we need to do, and that is substitute the actual value of capital back into this formula. So our final marginal product of capital will be 1.5 times 25 to the minus 0.5. And if you want to be lazy, you can just pick up the calculator and put it all in. 1.5 times 25 to the power of minus 0.5. And the answer will be 3/10, which is exactly 0.3 after you press the SD button. Similarly, what happens in the case of marginal product of labor? Well, the definition is differentiate the production function with respect to labor while capital is held constant. Now, my capital is constant, and in this case, the capital is now 25 because I've been given that value. So what does the actual production function look like as a function of labor only? So Q then now will be 25 to the 0.5 times L to the 0.5. Similarly as before, the 0.5 power is the root. So this is basically root 25 times L to the 0.5, which is 5 times L to the 0.5. So to find the marginal product of labor, all I need to do now is differentiate 5 L to the 0.5. So again, the differentiation rules. Keep the constant multiplier, bring the power down, and lower the power by 1. But same case scenario as above, the 0.5 will become minus 0.5 after taking 1 away from it. So 5 times 0.5 gives you 2.5 L to the minus 0.5. Again, this is the marginal product of labor function because it still depends on L. But the question was, what are these marginal products in the given specific values of capital and labor? So we need to substitute back L into the function. So the final answer is 2.5 times 9 to the minus 0.5. And again, use the calculator. 2.5 times 9 to the power of minus 0.5. And that gives you 5/6, which is not an exact function. It's 0.8333 recurring, but we can round it to 0.8 to 1 decimal places. So the key is here, when you're calculating the marginal product of capital, you keep labor constant. And usually that labor is given to you, so you can just substitute that back into the original production function. So you will be able to reduce the production function just as the function of capital. Then differentiate it and substitute back the given value of capital. Same for the marginal product of labor, because the marginal product of labor is the change in labor when capital is constant. So again, substitute back the constant value of that capital into the original production function, so you can reduce the production function as a function of labor only, then carry out the differentiation, and then substitute back the actual labor value to find the marginal product of labor for producing 9 units of good. So that was the marginal product of labor and the marginal product of capital applied to 2 different types of production functions. Let's move on and see how we can calculate marginal cost. So given a cost function, CQ equals 150 plus 12Q plus 5Q squared. What is the marginal cost function? So the marginal cost function, by definition, is the derivative of the total cost with respect to the quantity. Now, This notation of C bracket Q is just telling you that the cost function is a function of Q, is a function of quantity, and then it's telling you the exact function of the quantity. But this cost function is actually exactly the same as the total cost would be, because remember, that's the fixed cost and this is the variable cost. So this is actually the total cost function. So you don't always use TC for the total cost, you sometimes just use C bracket Q. But what it tells me that I need to find the marginal cost is I have to differentiate that cost function with respect to the quantity. So this is a cost function of 3 terms. Let's go about it and differentiate it term by term. The first term is a constant. Constant's derivative is 0. Well, that's nice and easy. I don't have to write anything down. The second term is 12q. Well, now q is exactly the same here as x would be. So when I'm differentiating with respect to q, 12q's derivative will be just 12. Remember, if it was 12x, it would become 12, but because now it's 12q, it also becomes 12. And the last term is 5q squared. Now that's a power. All I've done, I've just changed x for q, but the rule is the same. Bring the power down, so 2 times 5 makes it 10, and lower the power by 1. So 2 minus 1 gives it 1, so it will be q to the power of 1, but we don't write out the power of 1. And that is the answer, because the question was, what is the marginal cost function? And this is a function because I have got the variable q in here. So the marginal cost function will be 12 plus 10q. One more example on the marginal cost. So for the cost function of CQ being equal 25 plus 3q plus 4q squared, what is the marginal cost of producing 5 units of output? So I need to do the marginal cost, but now for a special case of q units of output being equal to 5. So first of all, I need to calculate the marginal cost function, just like in the previous example, and then substitute the q's value back into being 5. So what is the derivative of this function with respect to q, which is my marginal cost? So 25 is a constant, constant's derivative is 0. 3q's derivative is 3 plus power, bring the power down, that 4 times 2 makes it 8, and q squared becomes q. So that is the function, but now I need to know the exact marginal cost for 5 units of output. So what I need to do now, I need to substitute the q for 5 in the marginal cost. So 3 plus 8 times 5. Well, 8 times 5 is 40. 40 plus 3 gives me 43. So the marginal cost of producing 5 units of output is 43. Now let's look at some more complicated questions. Let's look at how to work out profit and profit maximizing level of output for a perfect competition. Now, when we're talking about perfect competition, there are a few things that we need to remember. Well, price is equal to the marginal revenue, which is also equal to the marginal cost. And also, what is profit? Well, profit is the difference between total revenue and the total cost. And total revenue can be calculated by price times quantity, and the total cost we can calculate by substituting the quantity into the cost function. Now observe that I've introduced something called Q star in here. Now Q star is the profit maximizing level of output. So we don't going to just substitute any odd Q into total revenue and total cost. We need to calculate a specific profit maximizing level of output to be able to calculate the maximum profit. So how are we going to go about that? Let's look at a practical example. You are a manager of a firm that sells its product in a competitive market at a price of 50. Your firm's cost function is C equals 20 plus 5Q squared. What is the profit maximizing output for your firm? Now there's a lot of things going on in here, but let's pick the question into parts and find out what are the most important things. Well, one of the most important things in here is that I am working in a competitive market. Competitive market means that I am a price taker. Okay? I have got no influence over the price. I have to take the market price, which means that I can only manipulate my own costs. So, in a perfect competition, one of the first conditions that you always have to remember is that the marginal cost have to be equal to the price. That's how I can start going on about the questions. The other thing, what other information do I have there? Well, a price is 50, so I know that P has to be equal to 50, and I also know the cost function is being 20 plus 5Q squared. Now I have got everything to be able to calculate the profit maximizing level of output. How? Well, there's the cost function, so I can calculate the marginal cost through differentiation. So this is my total cost function. So how am I going to differentiate this? Well, 20's derivative is 0 and 5Q squared derivative is 10Q. And this is my marginal cost, which is 10Q, and that has to be equal to my price because I'm in a perfectly competitive market, which means that this 10Q, my marginal cost, have to be equal to my price, which is 50. Well, that's simple enough. If 10Q is 50, then Q have to be equal to 5. And that is my profit maximizing level of output. And that is the answer to this question. Let's take it one step further and calculate the maximum profit. So you are a manager in a perfectly competitive market. The price in your market is 16. Your total cost curve is CQ equals 15 plus 2Q plus 0.5Q squared. What level of profits will you make in the short run? Okay, again, information. Perfectly competitive market. So the marginal cost have to be equal to the price. The price is given to me as 16 and the cost function is given to me as 15 plus 2Q plus 0.5Q squared. And the question is the profit. So profit is equal to total revenue minus total cost. For that, I need to calculate the total revenue first, and then I need to calculate the total cost. So the total revenue, remember, was price times Q star, and the total cost was the cost function at this Q star level. So first of all, I need to find this Q star, and this Q star was the profit maximizing level of output. How were we able to calculate that? While using this condition of working in the perfectly competitive market. So first I need to calculate the marginal cost, which is the derivative of the total cost with respect to quantity. So I'm going to have to differentiate this function with respect to Q. So 15's derivative is 0, 2Q's derivative is 2, 0.5Q squared's derivative. Now, it's a power function, so bring the power down. 2 times half is just 1, and Q squared becomes Q because I'm lowering the power by 1. So the marginal cost is 2 plus Q. But that marginal cost have to be equal to the price because I'm working in a perfectly competitive market. So this 2 plus Q have to be equal to 16. That's simple, because then that means that Q have to be 14. So I found the profit maximizing level of output. But that's not the end of the question, because I need the exact profit. So Now I need to calculate the total revenue, which will be price, which was 16 times 14, which is 16 times 14 gives me 224. And I also need the total cost, which was the cost function at this particular level of output. So what I need to do now, pick up this 14 and substitute that back into the cost function. So that will be 15 plus 2 times 14 plus 0.5 times 14 squared. Again, bring the calculator to help. 15 plus 2 times 14 plus 0.5 times 14 squared. That's going to give me 141. And then the profit will be the total revenue, which was 224, minus the total cost, which was 141. So 224 minus 141, and that gives me 83. So the profit, the maximum profit I can get is £83. Now let's look at one more of this profit maximization question, because this is involved quite a few different steps in the calculation. So you are the manager of a firm that sells its product in a competitive market. So again, as soon as you hear competitive market, you need to remember that the marginal cost always have to be equal to the price. At a price of 60, so again, we know the price in the market. Your firm's cost function, handy, so we'll be able to calculate the marginal cost. And that is 10 plus 5q squared. And what is your firm's maximum profit? So again, the profit is the question. So, to be able to calculate the profit, we need the total revenue and the total cost. Remember, the total revenue was price times the profit maximizing output, and the total cost was the cost at this profit maximizing level of output. So to be able to calculate the profit, we need that profit maximizing level of output. Where did you find it from? The condition of working in a perfectly competitive market. So first, I need to calculate the marginal cost. That is the derivative of the cost with respect to the quantity. So that's my cost function, simpler than the previous one. So 10 plus 5q squared. What's the derivative of this? 10 is a constant, its derivative is 0. 5q squared is a power function, so bring the power down. 5 times 2 gives you 10, and q squared derivative just going to be q, because 2 minus 1 makes it 1. So that's a very simple marginal cost function, 10q. That has to be equal to the price. So 10q have to be equal to the price, which is 60. So q going to be 6, and that is my profit maximizing level of output. Now I've got this profit maximizing level of output, I can calculate the total revenue and I can calculate the total cost. So the total revenue will be price, which was 60, times 6, so that gives me 360. The total cost is, remember, the cost function at this particular level, so I need to substitute the 6 into the cost function, so that is 10 plus 5 times 6 squared. Again, pick out the calculator to save some time. That gives me 190. And then the profit is just that 360 minus 190. Which is 170. So the profit is 170. Now, because these profit maximizing questions are quite long, I think it's a good idea for us to summarize the steps in the question. So how many steps and in what sequence should we carry out these calculations? So first of all, when you are trying to find either the profit maximizing level of output or the maximum profit, the first step always going to be to calculate the marginal cost function. So you would need to differentiate the cost function with respect to the quantity as the first step in every of these type of calculations. And then in step 2, you need to use the condition of working in a perfectly competitive market of marginal cost being equal to price to find the Q star, which is the profit maximizing level of output. Now, if the profit maximizing level of output was the question, then you can stop here because you already found that output. That would be your Q star. But if it's the maximum profit that is the question, you have to move on. So the third step would be calculating the total revenue by multiplying the price and Q star together. The fourth step would be calculating the total cost. Remember, all you need to do here is go back to your original cost function and substitute Q star into this function. And the last step is quite simple. To calculate the profit, you need to find the difference between the total revenue and the total cost. So you just take away those two quantities that you found in step 3 and step 4. You sometimes have to calculate the maximum profit of a monopolist. Now the monopolist works similarly, but instead of the cost, now you can manipulate the revenue, because remember, the monopolist is a price setter. It's not a price taker, it's setting the price. So it has got that privilege to saying, okay, I want to maximize my profit, so I'm going to do so by setting the price. So in that, instead of the cost function, you would be working with the revenue function. But the calculations are very, very similar. So I'm pretty sure you will be able to work it out yourself. But if not, or if you're having any problems, don't forget to get in touch. My contact details are on the slide.